Alright guys, so we are about ready to start our next unit in physics, and after spending all year on mechanics stuff, so that's the study of motion and forces, momentum, and energy, we're going to move on to another topic in physics. So a lot of what we're talking about in mechanics involved looking at mass and how mass affects the behavior of an object when a force acts on it. This next topic is looking at another property of matter, and that is called charge. So this is the introductory video, and just to get started, we will talk about conductors, insulators, and this idea of electric charge. Now, you guys have probably heard the stuff before. I may not be telling you much that's new, and that's okay. And, I think it's always good to hear stuff that you're familiar with. But just bear with me, and I hope that you gain some new knowledge in this video, and we'll talk more about it tomorrow in class. So, types of materials. When we look at materials, and as I said, charge is a property of certain types of matter. And when we look at these, what are called bulk materials, these materials that we can see, that we can hold, there is a class of materials which we have classified as conductors. And even if you don't know what the atomic or molecular structure of these things look like, we can still classify something as a conductor just from the fact that it allows an electric current to pass through them fairly easily. And some conductors, can pass a current through more easily than others. But nevertheless, this whole class of compounds, if we apply what's called a voltage to it, current will flow through it fairly easily. And these are typically things like metals. Copper, aluminum, gold, silver are examples of this. Gold is actually an excellent conductor. It's used a lot in high-end speakers and audio, inputs and jacks. Something else that's a conductor that is actually kind of strange is graphite. Now, graphite is not a metal, it's actually carbon, but the way that the carbon is bonded together, it forms these sheets, as you may remember from your chemistry class, and the electrons in these sheets can flow, they kind of form kind of like a wire, and they can flow fairly easily. So the graphite in your pencil is actually fairly conductive to electricity. So then there's the other class of compounds, which we call insulators, and this is when you put a voltage across them, current doesn't pass through them easily. It's not that current can't get through them, it's that it's extremely difficult for them to pass a current through. So they're called insulators. A lot of times we'll put this around a conductor, so we'll have, like, say, a wire, and we want to protect it from coming in contact with other wires. We want to maybe protect ourselves from touching the wire and getting a jolt. So we'll put an insulator around it, and these types of things are plastics, rubber, wood, possibly dry or oiled cloth. That's what they used before they invented plastics. And electricity can't pass through this very easily. One of the things I want you guys to know about both of these is why this is. What makes a conductor conductive, and what makes an insulator insulating. And I'm not sure if you've had this in sophomore chemistry or not, but if not, this will be new to you. So this is a conductor, and we're going to imagine that we're going to zoom in, and we're going to look at the conductor at the atomic level. And so what we would see is that as with everything else, this is made up of a bunch of atoms. Now, these atoms are arranged in here. I'm not going to fill all this up, but they're arranged so that we have our little nuclei in the middle, and then we have electrons close to it, and all that's pretty tightly held together. And then on the outside, we have what are called our valence electrons. So in metals, it turns out that our valence electrons in metals give away their electrons fairly easly. If you remember, again, from chemistry, when we talk about like sodium and how it likes to lose an electron in a reaction. So and all metals are like that. Metals tend to like to give their electrons away. And so these electrons are very loosely held. And so if you give this a little bit of a push, okay, so if you put, and we say an electrical push is a voltage. So if you put a push across this, because these are loosely held, these electrons can start moving through the material. Okay, so maybe this will be like a high voltage on this side and then a low voltage on the other side. We'll talk more about voltage later on in the course. But for right now, I just want to make the point that the electrons are loosely held. Okay, and then they are able to flow, able to move because of that. All right, so that's why a conductor is a conductor. And then as far as an insulator goes, we have these same, we have these same nuclei. But now what happens is instead of being very loosely held, these electrons are very tightly held to the nuclei. Okay, it's kind of like they're glued onto the atoms. So even though you can apply voltage, even though you can apply a push to this still, okay, if we have a high voltage on this side and we have a low voltage on the other side, you can apply a push to this, but these are so attracted to the nuclei in the middle of the atoms or molecules that make this up that the electrons won't be able to move. Like they're attached to the atoms. And because they can't move, they won't be able to conduct a current, because that's what current is. Current is the motion of charge through an object. Okay, so again, conductors, insulators, the reason why one conducts electricity and the other one doesn't has to do with what's going on at the atomic and molecular levels. So this concept of electric charge, mass, is easy for us to understand because we have mass. We experience the effects of forces on the mass, in our bodies all the time. But we're not charged. We don't have a net charge. Okay, we are neutral. It's not that the atoms that make us up don't have charges in them. We have nuclei, our positive nuclei, we have our negative electrons, but it turns out that most of the time, the number of electrons in our body, the number of protons in our body, they're the same. They even each other out. And therefore, when you add up all the charges, you're going to get zero, and we say that that's neutral. Sometimes this doesn't happen, especially at this time of year in the winter. You walk across the floor, maybe you rub your feet across the floor, you start picking up some extra electrons, then you touch the doorknob, and those electrons jump from your hand to the doorknob. Okay, so the unit that we use to measure electric charge is the coulomb. Okay, and 1 coulomb charge, as you'll see in just a sec, is like really a lot of charge, but that's the fundamental unit. It's called the coulomb. And one point I want to make to you guys is that electrons are the only charges that are transferred between objects. Those protons are held very tightly in the nuclei. They are not going to go anywhere. But again, using that rubbing your feet across the floor example, what's happening is electrons are being transferred between the carpet and the floor and your foot. And when that happens, you either have an excess of electrons if the electrons jumped onto you, or it's possible that the electrons in you jump down on the floor. And if that happens, then you have a positive charge, not because protons jumped onto you, it's because the electrons jumped off of you. Okay, so keep that in mind. Electrons are the only thing that is transferred between objects. Protons are never transferred. And when something gets a positive charge, it means that it has lost electrons. Now, as I said, the unit of a coulomb, it's a lot of charge. And to show you why that is, let's look at the charge of a single electron. This is the smallest unit of charge that things can come in. And the charge of a single electron is 1.60 times 10 to the minus 19th coulombs. Okay, now unlike mass, charge comes in two flavors. There's a negative charge and there's a positive charge. For historical reasons, which we'll go into later, the electron is negative. So the charge of an electron is 1.60 times 10 to the minus 19th coulombs. It's a very, very tiny charge. And these are like the little packets. You can't have a change in charge less than that because, again, charge is transferred in terms of electrons. And then The proton would have the same magnitude, so it's this 1.60 times 10 to the minus 19th coulombs, but it has the opposite sign. So the charge of a proton would be a positive. We don't usually write the positive, but it'll be 1.60 times 10 to the minus 19th coulombs. Okay, and that's what's in our nucleus. All right, so we are going to talk a lot more about this tomorrow. I'm going to show you some examples of how we can charge objects. And if you guys have any questions, please let me know.